Hello and welcome to the presentation component of the pavement construction report for the Riverview Bypass Pavement Construction Project. This is for assignment 3 of Pavement Construction Unit 602. The background of this project is it is a proposed bypass road around the Riverview town site. The drivers for the project is to reduce truck traffic within the town site and better service amenities to the north, being medical, educational, commercial and retail services. The bypass is to consist of 8 kilometres of total bypass road, being separated into a northern and southern section, 3 kilometres for the northern section and 5 kilometres for the southern, being separated in sections due to the northern area being in a low-lying, formerly floodplain area, i.e. different conditions essentially for construction. The bypass is also going to consist of 2 new intersections tying the bypass in with the existing river highway. The bypass itself, the makeup will be a single carriageway with 3.5 metre lanes in each direction and a 1 metre sealed shoulder with overtaking lanes for both the north and south directions, with the overtaking lanes being within the southern section of the proposed bypass. The aim of the construction report is to provide materials and construction specifications for the pavement sections within the proposed bypass, being the northern, southern and intersections. This consisting of details on the subgrade, subbase, base course, surfacing layers and drainage within the pavements. Also to identify key risks and safety and environmental considerations. With this presentation is providing a summary and highlighting the key elements of the report. Being in regional WA, the project specifications will be relating to Main Roads Western Australian specifications. The specifications up there on the screen with several specifications applying, being quality management, earthworks, culverts, pavements, bitumen surfacing, asphalt wearing course, in situ stabilisation, and the design of road pavements. Here's a summary of the provided data for the project. We have the overall bypass length of 8 kilometres, lane width of 3.5 metres with the 1 metre sealed shoulders, an operating speed of 100 kilometres per hour. The subgrade for each of the sections, we have the northern section, which consists of a low-lying silty clay subgrade with a soaked CBR value of 3, so fairly poor subgrade. The southern section is in a raised area with dense sandy subgrade soils with a soaked CBR value of 10, so a fair bit higher quality subgrade in the southern section. With the design traffic values being provided of 8 times 10 to the 6 ESAs for both the northern and southern, and then at the intersections, the intersection leg going towards the existing township, with obviously a reduced traffic volume of 5 times 10 to the 6 ESAs. Now, to fully consider the project construction report, we've had to make a few assumptions about the construction. These consist of the design traffic values provided, assumed to be for a single direction of traffic, i.e. directional factor of 1. The spray sealing is to take place in a dry period, i.e. warm, dry conditions. The traffic volume is expected to be over 600 vehicles per lane per day, being between 151 and 1200 vehicles per lane per day. This is important for our spray seal assumptions or spray seal design. The bypass road pavement is to extend 0.5 metre past the sealed shoulder, i.e. so the 9 metre seal consisting of the 2 3.5 metre lanes with 1 metre sealed shoulders on a total 10 metre formation. And we're also working on the assumption that there's an asphalt plant located in the Riverview town site for the supplying of asphalt for the project, and the contractor is to provide materials, i.e. the subbase and base course materials, having access to a local gravel pit. The assumption being typically regional WA having gravel products only available in the regional gravel pits. However, the contractor and gravel pit can provide Main Roads quality compliant materials, i.e. they have the capability to crush and screen and provide the suitable grading required for the respective pavement layer materials. Now, the northern section of the project is the low-lying, formerly floodplain area with the poorer quality soils present, again consisting of silty clays with some high plasticity clays sensitive to moisture changes, with the soaked CBR value being 3. Now, with this CBR value being quite low and high plasticity clays, subgrade treatment or improvement is required. Now, as per main road specification or engineering road note 9, clays of this nature assumed 2.5 to 5% untreated material swell. It does require a 600 millimetre of clean inert fill over the clay. This to cater for, I guess, the clay shrinking and swelling and not cracking the pavement. Now, this is quite a high requirement and quite potentially unachievable and costly exercise in regional WA, supplying that kind of quantity of fill material for regional road projects. So I've also considered an alternate which would, I guess, technically non-compliant to main road specifications but could be approved by exception, being a lime stabilisation of the in situ subgrade. So on the assumption that being a silty clay is likely more than 25% passing the 0.25 metre sieve, and that a 200, an assumption that the lime stabilisation could be achieved with a lime stabilised material CBR value of 15%, that a 250 mil lime stabilisation of the existing subgrade would achieve an ultimate design CBR of 9.5. So this is utilising Ostrode's equation 54 to calculate this. The resulting pavement designs for the northern section of road pavement are shown. Now, the main roads compliant design, which is the 600 mil of non-reactive fill over the in situ silty clay, obviously with the design CBR of 10, results in our primer seal, 170 millimetre gravel base course, 160 mil gravel sub base, the 600 mil of fill on the prepared in situ subgrade. Now, alternatively, if we go with the lime stabilisation option, we're sticking with our primer seal. Similarly, a 170 mil gravel base course and 160 mil gravel sub base. Noting they're the same, although the design CBR for the main roads compliant option is 10 and the lime stabilisation is 9.5. When we round the values up for the design CBR of 10, it does cater for the 9.5 CBR as well, hence why they're the same. And then the 250 mil of lime stabilised subgrade. At the intersections, you'll note the pavement thickness is slightly greater. Now, this is due to main roads engineering road note 9 requirement that intersection traffic volumes are multiplied by a factor of 3 to cater for the turning and braking forces expected at the intersection. So this multiplication factor of 3 was actually applied to the intersection leg, being the lower traffic volume, which would be where the volume of traffic essentially turning at the intersection to get onto the new bypass and continuation of the highway. So resulting in a slightly thicker pavement, 10 mil thicker in both base course and sub base. And then just to highlight the primer seal selection as opposed to a prime and seal, the primer seal was selected due to enabling early trafficking for both at the intersections for the road staying in use after hours basically, but also the neighbouring farming properties and accesses there. So expecting that early trafficking will be required. A cutback primer seal can be used for the bypass sections as the laying conditions being warm and dry is favourable and no subsequent seal being applied. However, an emulsion primer seal will be selected for the intersections with an asphalt wearing course being applied soon after. Obviously, the cutback not being suitable because the volatiles won't escape the seal before it's asphalted. And the intersection asphalt selected being a 40mm AC 1475 blow, which is a typical main roads intersection mix. A bit more heavy duty with the AC 14 just to cater for the heavy vehicles turning and braking on it. Now, the southern section of road pavement is much more favourable in terms of the geotechnical outcomes, having higher quality soils consisting of dense sand in elevated ground and with a 4-day soak CBR value of 10. Now, no subgrade improvement is required in this case, being quite high quality existing subgrade. So essentially the in situ subgrade would be prepared, strip topsoil, compacted and trimmed to the specification to then receive the subsequent pavement. Now obviously the pavement designs are very similar to the northern section in regard to the sub-base base course and wearing courses. So again, consisting of a 10mm primer seal, 170mm gravel base course, 160mm gravel sub-base on top of the prepared in situ subgrade, as opposed to the 600mm sand fill or a lime stabilised subgrade. And again, the intersections consisting of the same as before. Now this table shows a summary of the construction materials, I guess an overview of the process and the plant and equipment involved in both the northern section and southern section pavements. Probably worth noting the sub-base, base course and surfacing in terms of the process and the plant equipment required is similar for both sections. The main differences coming in the subgrade. So the southern section being much more simple in terms of the preparation of the in situ dense sands, requiring simply a grader, water cart and vibrating steel drum roller to prepare in accordance with the specification. But for the northern section, obviously we either prepare the in situ clay subgrade, which require a pad foot roller in addition to the grader, water cart and steel drum to enable appropriate compaction of the clays, to then receive the 600mm clean fill. Alternatively, the lime stabilisation option, which will also require a pad foot roller, but also the spreader truck and stabiliser for the lime stabilisation process. Noting the material quantities are a bit higher in the southern section, obviously being a 5 km section as opposed to the 3 km section, but probably worth highlighting the 600mm of clean fill required in the northern section is about approximately 18,000 cubic metres, which is be quite a substantial cost, hence why the lime stabilised option might be more desirable. So pavement drainage required throughout the project will consist of roadside open drains, similar to what's shown on the left hand side there for the southern and throughout. So an open drain with sufficient freeboard to the base of from the top of water level to the subgrade surface to help ensure there's no moisture ingress into the pavement. Now for the northern section though, being a low-lying area where groundwater may be a concern and or groundwater and perched groundwater, the addition of a longitudinal subsoil drain similar to what's shown in the diagrams there will be required to help ensure that no moisture is getting into the pavement and affecting the longevity of it. Key specification requirements for the project are highlighted, being separated again to the northern and southern sections. Sub-base, base course and surfacing all very, very similar, being same materials at kind of same thicknesses and everything. So 96% dry density ratio and 85% OMC for dryback for the sub-base, and 98% compaction and 70% dryback for the base course. Now the subgrade is where it differs the most. So with the northern section being clay and or lime stabilised subgrade, 92% dry density ratio applies with an 85% dryback. However, the southern section being sand, a 96% dry density ratio applies. However, dryback's not applicable, being a free draining sand in compliance with main road specifications. Now, the key risks for the project shown in the below table. So going over that, we have the workability of the northern section, obviously being in a low-lying area that's saturated subgrade conditions might be an issue for trafficking with construction vehicles and the preparation of the subgrade. So the mitigation strategies around that will be scheduling the works for a dry period, potentially considering a working platform and or temporary drainage throughout those sections. The culvert construction, so the culvert over the Black River in the northern section again, potentially have flowing water and or saturated conditions, being in the low-lying area of a watercourse. So again, be looking at scheduling the works for a dry period, and also having a dewatering management plan in place should dewatering be required. Pavement tie-ins and drainage, so the interface between different pavement types at the intersections, or at the intersections themselves, tying in old pavements with new is a potential point of moisture ingress. So the pavement tie-ins need to be considered, and potentially introduction of subsoil drainage at these locations. Traffic management is another main item, so both within the work site on the bypass road for local traffic access, being the farmers, farm accesses and construction vehicles. So having a TMP in place to restrict access and restrict speeds within the work area, ensuring obviously no damage to the pavement under construction. Then also the traffic management though at the intersections, the intersections being the higher trafficked areas where the existing road is going to be continuing to operate. Consideration potentially around different pavement types at the intersection being deep lift asphalt. This will minimise construction timeframes, but also aftercare traffic management with the deep lift asphalt essentially being trafficable each night. Alternatively, considering maybe even a minor bypass road at the intersections to have traffic completely separated from the intersection while the construction takes place. And also material segregation, so due to poor stockpiling, delivery and placement. So there's a few control measures or mitigation strategies listed there around that. Last but not least, the safety and environmental considerations to the project. So dust has been highlighted as an issue as the neighbouring crops are sensitive to dust pollution and contamination. So dust management plan to be prepared prior to works, which may include the dedicated use of water carts for dust suppression, potentially working restrictions when wind speeds are excessive. Flora and fauna, so there's been high value vegetation and wildlife identified adjacent to the site. So probably looking at having the work site and extent clearly defined and no entry to areas that might disturb or destroy high value flora and fauna, and having the appropriate environmental assessments and management plans in place. Acid sulfate soils is a potential risk, may or may not, but worth having an acid sulfate soil and dewatering management plan in place just in case, particularly the area of the culvert crossing where there'll be excavation into the low-lying subgrade materials. The waterway itself at the culvert, there might be the need for a temporary river diversion or bunding and appropriately dewatering. So again, having a dewatering management plan in place. Traffic management in general, which we've discussed about, but obviously a high safety concern. And then any existing services, so service disruption and costs relating to damage caused to existing services, obviously a high risk and safety concern. So conducting the appropriate investigations prior to works and locating any existing services and ensuring safe work practices in line with the relevant service authority requirements to complete the work. That's it for this presentation. Thank you for your time.